In a previous video, we saw that if you run an electric current through a wire, then it can deflect a magnetic needle kept close to it. This means a current-carrying wire can push on a magnet. But Newton's third law says that for every action, there must be an equal and opposite reaction. So, if a current-carrying wire can push on a magnet, then that means a magnet can also push on a current-carrying wire. So this wire must also experience a force due to this magnet. And in this video, we're going to explore the properties of this force. Well, first, let's think about how the magnet is pushing on the wire. Well, remember how we said the wire was pushing on the magnet? We said that whenever a wire carries current, it produces its own magnetic field. And we said it's that magnetic field that pushes this magnet. Now, similarly, how can we answer the question, how does the magnet push on the wire? Well, we can say the magnet also produces its own magnetic field. So let me get rid of the field of the wire and let me bring back that needle. So the magnet also produces its own magnetic field, which may look somewhat like this. And it's that magnetic field that is pushing on this wire. So this means, in general, we can say that whenever we have a current-carrying wire or a current-carrying conductor in a magnetic field, it experiences a force. So magnetic fields not only push magnets, but they can also push current-carrying wires. And that kind of makes sense because we've seen in previous videos that current-carrying wires sort of kind of behave like a magnet. And so it makes sense that they would be affected by magnetic fields. And this is awesome because now magnetic fields can push on current-carrying conductors and make them move. This means we can now you can now use electricity to make something move. And this is the principle behind your electric fans or your electric cars or any electric machines. Where we use electricity to move something, it is by using this principle. You just place it in a magnetic field and the magnetic field will push that conductor. But before we can do anything useful with this, let's first learn the properties of this force. Like, what does that force depend on? What direction is that force acting over here? Things like that. And so to figure this out, people performed experiments in which they placed this wire in a uniform magnetic field. Not like this. A field where the field strength and the field direction is same everywhere over the wire so that we can understand exactly how the field affects the wire. You can see over here, the field on this wire is not uniform. Its direction is also continuously changing over the wire, right? So let's place the wire in a uniform magnetic field and see how it affects the wire. So to produce a uniform magnetic field, all we will need are two giant poles of a magnet. And so now if we look at the field in between these two poles, you may recall the field always starts from north and ends into the south outside the magnet. The field will look somewhat like this. And you can see that in this region, the field is pretty uniform. You can see the direction of the field is same everywhere. And the field, the crowdedness of the field lines is also same pretty much. They are pretty much equidistant everywhere, right? So the field strength is also same everywhere over here. And so now we can place a current carrying wire over here and perform our experiment. And if you're wondering, how do we get two poles like this? Well, then you can do two things. Either get two giant bar magnets, one for this and one for that, and keep it over here. Or we can use something called a horseshoe magnet, which looks like a horseshoe, which is shown over here. And you can see the poles of a horseshoe magnet are apart, just like what we need. All right, so now let's place our current carrying wire in this magnetic field. You can pass the current through it by attaching it to a battery, which I have not shown over here. And then we can perform experiments and see what does that force depend on. The first thing people wanted to check is, how does the force depend on the strength of the current? And I want you to sort of guess this. What do you think will happen to the force acting on this wire if the strength of the current was to increase? What do you expect? Well, we know that a current carrying wire is sort of acting like a magnet, and that's why it's being affected by the magnetic field, right? Now, if you increase the current, then it'll become sort of like a stronger magnet, isn't it? So you would expect the force to increase. And that's exactly what we found out. We found out, so this is result number 1 from our experiment, is that if you put more current through that wire, it'll automatically experience more force. So you can increase the force just by increasing the current. If you decrease the current, the force will decrease. If you make the current 0, the force will vanish. The second result is not so obvious. What they found is that the force acting on this wire not only depends on the current, but it also depends upon the angle between the wire and the magnetic field. What they found is that when that angle is perpendicular, when the wire is perpendicular to the field, like we have kept over here, that's when the force is maximum. So right now, the force on this wire is maximum. But if you were to keep our wire this way, place the wire this way, then even though the current is the same and everything else is the same, turns out that the force will reduce because the angle has decreased. This is very important, and this is not at all obvious. But experiments show us that. And if you were to decrease this angle further, the force will decrease. Just look at this angle between the wire and the field. The force will keep on decreasing. And eventually, if the angle becomes 0, if we make our wire parallel to the magnetic field, the angle becomes 0, the force vanishes. The force becomes 0. I've not written that down, but we can remember this. And this is super important to remember. So the force depends on the angle. If it's 0, the force is 0. As the angle increases, the force increases. And when the angle reaches 90 degrees, that's when the force turns out to be maximum. The last thing we'll talk about is the direction of the force acting on this wire. Now, we will figure out the direction of the force in a separate video. All right, we'll do that in complete detail in a separate video. But the question over here is, what do you think the direction of the force depends on? Again, pause the video and think about this for a while. All right. Well, experiment shows us that the direction of the force acting on this wire depends on 2 things. It depends on the direction of the current, in which direction the current is going. So if the current is going upwards, the direction of the force will be in one direction. If the current is going downwards, the direction of the force will reverse. And it also depends upon the direction of the field. If you reverse the field, turns out again the direction of the force will reverse. But don't worry too much about this third point. As I said, we will discuss about this in great detail in another video. So, what did we learn in this video? We learned that a current carrying wire placed in a magnetic field experiences a force. And using this, we can now convert electricity to motion. And we learned a couple of properties of this force. We saw that more the force, more the current, more the force. And we also saw that the force is maximum when the wire is kept perpendicular to the direction of the field.